In today's lesson, we are going to be graphing exponential functions. So we're going to be looking at some graphs, how the equations relate to graphs, and just some general properties of the graphical representations of exponential functions. So we're just going to kind of get into it. We're going to graph each function. We're going to state the domain and range. We're going to state any intercepts. We're going to determine whether there's intervals of increase or decrease. And then we're going to look for the equation of any asymptotes. So we have our equation for this exponential function y equals 4 times 1/2 to the power of x. So this means that if I have x values, I can create a table. So I'm going to say -3, -2, -1, 0, 1, 2, and 3. We should recognize that this 4 represents our initial value. So that means at 0, we have 4. And this half is our decay factor, right? Because it's less than 1 and between 1 and 0. So that means that as I increase, I'm dividing by 2, or I'm taking half of everything. Or you could say that you are multiplying by 1/2, which is the same thing as dividing by 2. So then the next one would be 2, then 1, then 0.5, because we're dividing by 2 or multiplying by 1/2 every time. Now to fill out the rest of my table, I could plug in my x values. So I could do 4 times 1 over 2 to the power of -3 and get an answer of 32. Or if I know what my pattern is, I can kind of reverse it. So instead of multiplying by 1/2, I'm dividing by 1/2, or you could say multiplying by 2. So I get 8, 16, and then 32. So different ways you can kind of fill out your table of values, depending on what the growth factor or decay factor is, and that will probably determine how you fill it out. If it's something nice like a half-life like we see here, or doubling or tripling, that tends to be easier to fill out rather than if it was, say, growing or decaying by 1%. So saying like your growth rate was 10%, right? It's maybe not as easy to fill out the table. But now that I have my table of values, I can go through and enter or plot the points and sketch my graph. So 0 and 4, 1 and 2, 2 and 1, 3 and 1/2, -1 and 8, -2 and 16, and -3 and 32 is off our scale. So we can just graph kind of what we have, but we get a general idea of how it's going to look. Right, so generally we have our exponential function here. And that is what this exponential function looks like. So now looking at that, let's kind of go through and determine the domain, the range, x-intercepts, y-intercepts, whether it's increasing or decreasing, and any asymptotes, just to kind of look at some properties of these exponential functions. So our domain, all the possible x values. So in this case, our domain, x is any real number. Right? There's no restrictions. It's going to continue along the x-axis either direction. For the range, and this one, y is also any real number. However, there are restrictions now. Right? We can see that there are no negative values. As well, we've talked about, could I ever, or will this line ever reach 0? Can I divide by 2 and ever get to 0? In this case, no. Right? You can't divide to get to 0. So this means that y is any real number given that y is greater than 0. Now keep in mind, we don't put the equal sign or equal portion of this because y will never equal 0. So y is only greater than 0. And we can see that because it will exist for anything above the x-axis. For x-intercept, does it ever cross the x-axis? We just kind of talked about that. No, it won't. Our y-intercept, we can see, is 4. Right? Or you can say the point 0, 4. Intervals of increase or decrease, well, it is decreasing. So this is decreasing. And when we talk about intervals of increase or decrease, we're looking at it as we go left to right. Right? So maybe you can put a note from left to right. So we can see in this case, as we go from left to right, so as we go in this direction, we can see that our values are decreasing. In terms of the asymptote, right, an asymptote is an imaginary line, it could be horizontal or vertical, that our graph approaches. And in this case, it is going to be the asymptote of y equals 0, which is a horizontal line, or you could say, you basically say it's the x-axis, which is just a horizontal line, and that is because our graph is going to approach it, but it's never going to quite reach that value, right? So we're never going to have a value of y equaling 0. This is the same thing as saying that our graph approaches the x-axis but never quite touches it. Let's look at the next example. Y equals negative 3x to the power of negative x. And again, a little bit of a typo here. Y equals negative 3 to the power of negative x. Let me just fix all of that just for make it a little bit neater. So y equals negative 3 to the power of negative x. Right, so this one is a little bit tricky. I could just plug in x values and go through and solve, but I do want to put this into more or a better form for an exponential function, so it's a little bit easier to kind of work with. Right, so I can actually rewrite this. If I think of there being this general form y equals ab to the power of x, right? If I think about, okay, well, I have a negative 3, so what two numbers could that be multiplying? Well, that could be negative 1 times 3 to the power of negative x. But I don't usually have a negative x in my exponential function. I haven't really seen anything like that. So how can we fix that? Well, from our power laws or our power rules, to get rid of a negative exponent, we flip our base. So in this case, I could actually write this as negative 1, and I flip my base 1 over 3, and now my x becomes positive. So this is actually a better representation of my exponential function. Right? And by looking at that, now I can see, I can see my initial value, I can see the decay factor in this case, and I can also see my x being positive. So I'm going to fill out a few values. There's more here than we really need. Do negative, we'll do the same ones, negative 3, negative 2, negative 1, 0, 1, 2, and 3. So I know I'm going to start at negative 1. Right? Because that's my initial value, that's that a value of our equation. Now the growth factor, or the decay factor, sorry, in this case, is 1/3. So that means that as we increase, we are multiplying by 1/3, or you could say dividing by 3. So if I take negative 1 divided by 3 or multiplied by 1/3, I get negative 0.33. Continue the pattern, divide this by 3 or multiply it by 1/3, I get negative 0.11. Now again, this is rounded a bit because we can't really enter these values, or we can't really do these calculations and get a nice round number, because 1 divided by 3 is negative, or is 0.3 repeating. And then if I go on to the next position, again, divide negative 0.11 by 3, and we are at negative 0.036, or 37, because it's 3, or the 6 is repeating, so we can round that to the 7. If I want to fill out the rest, I can go back up actually, and instead of multiplying by 1/3, I'm going to divide by 1/3. Or you could say, if I'm dividing by 1/3, that's the same thing as multiplying by 3. So negative 1 times 3 is negative 3. Negative 3 times 3 is negative 9, and negative 27. Now that I have my table, I can go through and plot my points. Can't really do the negative 3, it goes off our scale, so that's okay. -2 and -9 I can plot. There. -1 and -3. 0 and -1. 1 and -1/3. And 2 and -0.11. I'm not going to be able to do 3 and -0.037. That's just too close to the x-axis. So I can sketch what I have right now. And we should again tell that it's going to get very, very close to the x-axis. Now, looking at this and based on what we know about transformations, this does make sense, right? Because the only thing that's changed, or our a value, is now a negative. And our a value before in transformations implied that there was a vertical reflection. Right? So you could think, if I look back at this one, this was a decreasing or an exponential decay. So if I think about reflecting it vertically, flip it over the x-axis, it would look something like this. So it does kind of make sense based on the function that we're seeing. Let's go through and look at our domain and range. So our domain, so x, again, can be any real number. There's no restrictions on x in this case. For y can be any real number, given that y is less than 0. So this one's different because if we look, y is getting closer and closer to 0, but it's coming in from the negative side. So y is going to be less than 0. Right? It's going to be any negative number up to 0. It's not going to get there. Our x-intercept, well, it's never touching the x-axis, so there is no x-axis, or x-intercept, there is none. Our y-intercept, again, that's our initial value. We can see where it's crossing the y-axis. This is 0, -1. Now, in terms of increasing or decreasing, again, remember we read it from left to right. So what's happening to our values as we go left to right? In this case, they're getting larger, or they're getting closer to 0, but they're coming from the negative side, right? So this is actually an increasing graph, or intervals of increase. Now, that might seem kind of opposite of what our function is, right, because of that 1/3, but we have to consider where we're starting, or that a value as well, because that will change things. Right? So even though it's a third, technically our values are increasing. And then our asymptote, again, in this one, right, we have an asymptote of y equals 0 because it is approaching the x-axis. So we have a horizontal line at y equals 0 that our graph or our function is going to approach but never get to. So hopefully you're seeing some connections between the function itself and some of these characteristics. We're going to move on, though, to looking at coming up with an equation for an exponential function from a graph. We have some step-by-step instructions here, so we can write the equation in the form y equals ab to the power of x. Again, that's our general function or form. We can start by determining the growth factor, right? Because in some cases you might say, well, why don't we start with the y-intercept or the a value, right? The initial value. That should be easy to see, right? However, depending on what the scale is, the a value might be small in comparison to some of our other values, especially because it's exponential. Right? So in some cases, it might not be easy to see the a value. So we're going to look at determining it algebraically so that we're certain what it is. So what we're going to do, though, is we're going to find some nice points on our graph. So we can see there is 1 and 6. We have, looks like 2 and 18. 2 and 18. And again, yes, this is a little bit subjective, but we should kind of see these nice points. And then 3 and 54. So now that I have those nice points, I can actually plug them into my table of values. So I can do 1 and 6, 2 and 18, 3 and 54. Right? I'm going to put in 0 here because that is what we're looking for. Right? We do need to look for 0 to get our a value or our initial value. We're going to look at two ways on how to do that. But we do want to look for our growth factor first. So a way that we can find our growth factor is if we look at what factor these values are increasing. Right? So a way you could do it is you could kind of like first differences, except you're dividing. You're finding the ratio. So 18 divided by 6 is 3. 54 divided by 18 is 3. So because they have the same ratio of 3, that tells us that our b value is equal to 3. Now, we'll look at our steps. Say the next step is after we have our b value, we're going to take our b value. Let me use a different color. We're going to take our b value of 3. We're going to take a random point, let's say 1 and 6, and we're going to plug that into our equation, y equals ab to the power of x. So we have 6 is equal to a times 1 to the power of, not 1, times 3 to the power of 1. And now I'm going to solve for my initial value, similar to what we've done in previous lessons. I'm going to bring this 1 over 3 over. It's going to become division. We're left with then 6 divided by 3 is equal to a, or 2 is equal to a. So now that we did it algebraically, now I can write out my equation, which would be y is equal to 2 times 3 to the power of x. Now, because we have nice values and because our growth factor in this case is a nice value, it's a nice growth factor in this case of 3, I could solve this a different way or find my initial value a different way, because if I'm multiplying by 3 every time I increase, if I decrease, I'm actually going to be dividing by 3. And 6 divided by 3 gives us 2. So different ways you could figure it out, right? Kind of like using a pattern that you may have done back in grade 9 to figure out and work your way back to the initial value. You can do the similar thing here. If we know what the pattern is, we can work backwards. Or if not, or if it's not a nice factor or growth factor or decay factor, we have the algebraic option as well. So based on what we've looked at, what do we know about when a function of the form y equals ab to the power of x is increasing or decreasing? So what do we know about this function? What do we know about these exponential functions when this is the case? And there's going to be 4 scenarios, right? So 4 scenarios where it's increasing or decreasing. And I'll help you out a bit. I'll sketch it. So if we have our axes, right? General one in terms of increasing, it'll look something like this. Right? That's our first general one for increasing. Right? We have our points. So what are the characteristics of this one? Right? We'll put down that this is increasing. Well, in this case, we want to look at 2 things: what our a value is and what our b value is, right? Because those are going to be the 2 things that we see in our function. In this case, our a value is going to be greater than 0. And because it's increasing, our b value is going to be greater than 1. So this is our standard kind of increasing exponential growth that we've looked at. On the flip side then, for decreasing, we can go back to our kind of traditional exponential decay type formula, where it looks something like this. And this would be an example of decreasing, right? Again, we've looked at this before. We've had a whole lesson on this, right? So this would be decreasing. And what characteristics do we see about our a and our b value? Well, in this case, our a is still greater than 0. And our b value in this case is actually going to be between 0 and 1, right? Standard kind of characteristics of exponential decay that we've seen already. Looking at the examples that we started with, though, in the very beginning, there are 2 other types where we could see an increase and a decrease with an exponential function. The other 2 if I have my axes, would be something like this. So I have my points. Now this, we looked at an example of this already. This is an example that is increasing. Right? The values are getting closer to 1. They're increasing. They're going from negative to positive. Sorry, not 1, 0. They're going from negative to positive. So this is an example of increasing. And again, what characteristics do we recognize about our A and our B value? Well, here we see that our A value is less than 0. So we have a negative A value. And what do we notice about the B value? Well, in this case, we should recognize, right, we kind of talked about it before, it's almost a reflection of this graph. So our A value is negative, that takes care of the reflection. So if our values are, if we ignore the negatives, so to speak, the numbers are very large and then they get smaller to decimals. So this would be something where we see actually a B value that would indicate a decay. But because of that A value being negative, it's actually a graph or an exponential function that's increasing. We wouldn't really call it exponential growth though. Exponential and growth and decay are kind of reserved for these top two. Let's actually kind of put that. Actually, I'm not going to put that in there just because I don't want us to get us confused and think that the other ones are also considered exponential growth and decay. So this is another example where we could have an increasing exponential function. And if I look at another example for decreasing, you can probably see where this is going. Another example for decreasing, so basically our numbers get smaller or larger or more negative, would be something like this. Just putting arbitrary points in there. Right? And again, looking at our A and our B value, we want to say, okay, well, our A value again is in the negative, so it's less than 0. But we should recognize that this graph almost looks like a reflection of this one. And if our A value being negative causes that reflection, then in order to have this shape, our B value would have to be greater than 1. So we're kind of looking at a little bit of transformations in this case. But we see that we have two different scenarios or possible values for A and B that could give us increasing functions, exponential functions, and two scenarios that could give us decreasing exponential functions. So we want to be aware that it's not just the exponential growth and decay that will give us increasing or decreasing functions. There are different, or there is like kind of like a reflected version that gives us an increase and decrease as well. So with that knowledge now, let's go through and just state the y-intercept, state whether it's increasing or decreasing, and then we'll make a rough sketch. So in this case, our A value is going to be 2. Our B value is 1/2. Right? So this is our standard kind of format for exponential decay. Right? So that means roughly our graph will start at 2, or y-intercept at 2. And it'll look something like this. We could get technical and we could plot some of the other points if we wanted to. But for sake of argument, we would just, the main thing is just more of a sketch. So just what's the general shape look like? And it would look something like that. And we could say that it is decreasing. For the next one, y equals 2 times 4 to the power of x. Again, looking at our values, our A value is 2, our B value is 4. Okay, this is one of our standard kind of examples of exponential growth. Right, so this would be increasing. And if I just wanted to quickly sketch it, we're at a factor, or our y-intercept of 2, and then we grow exponentially by a factor of 4. So the next one would be 8, and then 32, and so on. But the main thing is just using our y-intercept and just kind of sketching roughly what it should look like. C is now where we're looking at some of those other examples. Right, we're still going to go through, find the y-intercept. In this case, it's -2. Our b value is 4. So this is kind of opposite or reflected of what we just saw, because that a value being negative. So I can plot that point, say -2. Now I have to think, okay, what is going to happen? Is it going to be increasing or decreasing? Well, you could think, well, that factor of 4, that should make my numbers larger. So if I'm starting with a -2, my next value is going to be more negative than that, right? So it would be -4 times 2, which is -8. So this means it would look something like this. Maybe something like this, right? Because as my x values increase, I'm going to get larger and larger negative values. So this would actually indicate decreasing. So intervals of decrease, you might say. And then for D, same idea. A value is -2. Our B value is 1/2. So I'm going to plot that just to get an idea. So -2. And because it's decreasing, or we're multiplying it by a factor of 1/2, that means that as the x values get more positive, or in the positive direction, my value should be getting smaller. -2 times 1/2 is 1. 1 times 1/2 is 1/2, right? 1/2 times 1, or 1/2 times 1/2 is 1/4, and so on. We can see that our values are getting smaller and smaller, closer and closer to 0, the more positive the x value gets. So this, when we look at it, is actually an increase, or it's increasing, because our numbers are technically getting higher and higher. They're getting less negative. And so this is actually increasing. So again, that was it for this lesson. So just the idea of looking at an exponential function, recognizing what the y-intercept is, recognizing what the b value does, to how it to help the shape of our exponential function, as well as these two other examples where we might have some reflections. And so that means that when we talk about increasing or decreasing, it might be, or it's opposite of what we kind of think. So we got to be mindful of what our a value is and what our b value is when describing the graph.